Welcome back to this Bits of Q series on template metaprogramming in C++. In the previous episode, we created our own tuple class with the accompanying makeTuple function as well as a get function. As we created the get function, we found that it is very easy to make mistakes when forwarding the elements of your tuple. So to help test our tuple, we introduced the CopyCounter class. By adding an instance of this class to your tuple, you can keep track of how many times it was copied, moved, or default constructed. We then used this CopyCounter to compare the performance of our makeTuple with the standard library version, by including it as a tuple element and requesting the stats after the tuple was created. As you can see in the terminal, both our own and the standard library version of makeTuple copy their input exactly once when it is passed as an lvalue. The get function, on the other hand, returns a reference, and since we did not assign it to anything in our test, we can see that no copies are made. Of course, a get function is not the most complex operation. So today we'll create our first real tuple algorithm. We'll be creating our own version of tupleCat, a standard library function to concatenate tuples. We'll first create a simplified version of tupleCat that only works on two tuples. So if you have a tuple of int bool called t1 and a tuple of double string called t2, we should be able to use our tupleCat function to create a concatenated tuple t12 with the type int bool double string and the values from the original tuples. So we will have to figure out the new output type at compile time, as well as the sequence of forward operations to get all the data into the new tuple in an optimal way. Let's open up the tuple header and give this a shot. We'll first define the tupleCat function as a variadic template taking an arbitrary number of tuples. We of course accept our tuples as forwarding references, and then we'll simply forward these tuples to a member function of the tupleCat impulse struct in the detail namespace. We'll just call it function f for function. This is a convention we'll be using more often later in this series when we dive into high-performance metaprogramming techniques. Now we define this tupleCat impulse struct with the function f, which we just passed our tuples to. As I said, we'll initially just support two tuples, so we'll give f two template parameters, tuple1 and tuple2. Since we'll be creating a new output tuple and returning that by value, you can simply use auto for the return type. We will now use a trick we've seen before in this series. We'll be creating an index sequence so we can construct this output tuple by repeatedly using the get function on the original input tuples. We'll call the function that actually does this concatenation using indices and the get function cut from indices. This function will take our two tuples and two index sequences for these tuples. We can use std_make_index_sequence and then pass the size of the tuple, which we can retrieve using tuple size v. Of course, the standard library defines a tuple size v, but we haven't done so yet. So we'll fix that in a bit. We do the same for tuple2, and that completes our function call. Quite a long line. Let me quickly save to trigger the automatic formatting. That looks much better already. Now to write a tuple size meta function. Template type name ... elms, and this is of course already the partial specialization, so let me first define the template itself. Template type name tuple, struct tuple size, and for the specialization we'll accept tuple of elms as the template argument. And here we'll just inherit from std integral constant. We haven't used std integral constant before, so let me quickly explain what this does. Integral constant is a template from the standard library that is used to define constant values of a certain integral type. The first parameter is the type, for example int, size_t, or even char or bool, and the second parameter is the value, and should of course be of the type of the first parameter. Integral constant then defines a member value with this value as well as a value type alias and some operators for convenience. We are only interested in the value member for our tuple size. Now, for convenience, we also define a tuple size v alias as tuple size : value. Now, I see I did something wrong here. I should of course be passing instances of make_index_sequence. That looks better. Now for the definition of cut from indices. This is again a template, taking our two tuples by forwarding reference. And now we get these index sequences. So we'll add two parameter packs, size_t ... indices1 and indices2. Allowing us to write the types of the third and fourth function parameters as std index sequence of indices1 and 2. We don't need to give a name to these last parameters, as we are merely using them so the correct template instantiation is chosen by the compiler. It's essentially a form of type dispatch. Now for the implementation. Since we defined deduction guides, we can create a new tuple here from the gets of t1 and t2, expanding the parameter pack resulting in the correct sequence of get function calls to copy all the input elements to the output tuple. Of course, to make sure we correctly handle rvalues, we should be using std forward here. Now, it is important to realize that as all these get statements get expanded, you'll be invoking the std forward function on the same tuple over and over again. In general, calling forward on the same input multiple times is really dangerous. If your input is an rvalue reference, the forward will act as a move, which usually destroys the input. So calling forward a second time on this now moved from input can lead to all kinds of undefined behavior. The reason why it is safe to do multiple moves of the same tuple in this specific case is because we know that the get function will only touch the element which we give it. Since we are only executing get on each element once, we know that the elements on which the get functions operate haven't been moved from before. In theory, this should be it for our 2-tuple version of tuplecut. But I already see a red marker on the right. I forgot to make our member function static. And now we get another error. Implicit instantiation of undefined tuple size on a bits of queue tuple. A reference. Stupid mistake. Luckily also easy to fix. If your tuple size doesn't work on references, then make sure you don't pass it a reference type. I will even use std remove cvref, as const tuples will also not work with our tuple size v. And now everything compiles. Great. Let's test if it also works as expected. We'll just assert that the get0 of t12 is 8, and that the fourth element is the string hello. And for good measure, let's also check our tuple size. Here we of course need a type, so I'll use decltype to get the type of t1, which should of course have a size of 2. I now realize I accidentally put tuple size in the detail namespace, so let me quickly move it out. I'll just define it here for now. And now back in our main, I'll add one more check for the tuple size of the concatenated tuple t12, which should be 4. And I'll also move these checks to happen before we actually do the get calls. And now everything compiles and the asserts pass. So now we have a 2-tuple tuplecut function that gives the correct output when passed 2 lvalue tuples. But you have no idea if it will also operate correctly when passed rvalues or const references. And we saw before that it is quite easy to make mistakes when forwarding values in your algorithms. So it's probably a good idea to test some different variations of lvalues and rvalues, const and non-const inputs, just like we did with the get function in the last episode. So we could repeat this test 4 times. Or if you really want to cover all cases, you should even do it 16 times. Once for each possible combination of 2 const, non-const, lvalue and rvalue input tuples. But that would lead to a lot of code duplication. So, as I said last time, I want to introduce a small test utility. A test framework, if you will, that will help us execute our tests with different types of inputs. Since I do not want to make this episode about these test utilities, I created them off screen, and they are already in the test utilities header. If you're not interested in these test utilities, feel free to skip ahead. There are timestamps in the description. The first change I made in the test utilities header was an upgrade to the CopyCounter class. I turned this into a template named indexed CopyCounter, which, as the name suggests, takes an index as a template argument. The reason for this is that it allows us to work with multiple CopyCounters simultaneously, as long as they have different indices. After all, different instantiations of the indexed CopyCounter template are different types, and as such, they'll have their own separate piece of memory allocated for the static stats member variable. The CopyCounter we've been using in our main file is actually an alias for this indexed CopyCounter, with some default index. I also created a make CopyCounter convenience function that creates a CopyCounter and does a reset for you. It uses a new constructor, which is invoked only when passed a special reset after construct type. Note that we can be sure that the constructed CopyCounter still has all its stats at 0 after it is returned from the make CopyCounter function, as since C+17 we have guaranteed copy elision when returning a PR value. In other words, no copy or move will take place when returning this thing, and as such the stats will not be incremented. Lastly, I added a comparison operator, allowing you to easily compare 2 different indexed CopyCounters, which will, under the hood, compare the associated statistics. If this all went a bit quick, don't worry. We'll see this new indexed CopyCounter in action in a bit, when we create our new tests. To create these new tests, we'll use the second and biggest change to our test utilities header, the little test framework in the testing namespace. Now, I should add a bit of a warning here. I created this test framework because I wanted an easy way to write tests for the algorithms which we will be developing in the upcoming episodes, without having to include a dependency to a third-party framework. And maybe also a bit because it was just fun to write this test framework. In general, however, for any serious project, I highly recommend using an established testing framework, such as Google Test or Catch, and not writing your own. That being said, this framework does have some nice features. It has its own assert statements, a way to create testers, or test executors, whatever you want to call them. And it even offers a way of invoking tests with different combinations of lvalue and rvalue inputs. I use several of the metaprogramming techniques discussed in the previous episodes, as well as some other more advanced C++ features explained in other videos on this channel, such as faults and requires expressions, to create this framework. I won't go into the details, but if you're interested, the code can be found on my GitHub. The link is in the description. For this episode, however, I'll explain the features of the framework by actually writing some tests with it, so we can continue the implementation of our TupleCat afterwards. First, we create a few aliases to make our code a bit cleaner. I'll define some const expr size t indices for use in our indexed CopyCounter. One for bits of q tuples and one for std tuples. I'll also add using statements for the tester and tester with builder classes. I'll show you in a bit what they're used for. Now I'll start by creating a new test for our tuple construction. I'll use the tester class for this and will execute the test member with a test name. In this case, I'll just call it constructor. To add the implementation for the test, we pass it a lambda. We create a copy counter for the bits of q tuple and one for the standard tuple, so we can easily compare them. Then we create a bits of q tuple and a standard tuple, and this is why I created the BOQ namespace alias, so these statements line up nicely. And then we compare the number of copies and moves made by simply asserting that C1 is equal to C2. If I now compile and run, we see all the outputs from before, but when I scroll up, we also see that the constructed test ran and the test passed. Those of you who are familiar with the Google Test framework might have noticed that I took some inspiration from that framework when it comes to formatting our output. Now let me also refactor the make tuple test so we can throw away all this old stuff. Again, creating two copy counters, doing a make tuple and an std make tuple, and comparing the copy counters. Simple as that. To test the get, we use the tester with builder instead of the normal tester. This will allow us to easily test get with const and non-const lvalue and rvalues without having to duplicate our test code. Let me demonstrate how a test with a builder works. Tester with builder is a template that takes as parameter the number of arguments the builder should create for the algorithm that you want to test. Since get operates on only a single tuple, we will just use one here. Again, we invoke the test member function with a test name. I'll call it builder demo for now, and then a lambda. But now this lambda takes a single argument, namely a builder. This builder allows you to create an instance of whatever type you want. I can, for example, say builder, build me a tuple of int bool with the values 42 and true. This lambda is then going to be executed multiple times with different builders, and each of these builders will return an instance of this tuple as a const, non-const, lvalue or rvalue. I can show this by outputting the type that's returned using boost type ID with CVR. As you can see, this builder demo is now called 4 times. Once with a builder that returns an lvalue reference, then a const lvalue reference, an rvalue reference, and lastly a const rvalue. And what's even better, if I need 2 inputs, for example because I'm testing a TupleCat function, I can just write something like this. Now the builder demo test will be executed 16 times. Once with a builder for every possible combination of const and non-const lvalue and rvalue pairs of types. So that's how you use tester with builder. Now let's use it for a get test. We need a builder for generating a single argument. We use 2 copy counters again, just like before. We create 1 bits of q tuple and 1 std tuple. And now we'll invoke the actual get call. we do have to make sure to forward the instances here. Otherwise, we still won't be testing with both the value categories. Finally, we just assert that v1 equals v2. Bam, get passes. Now note that I am comparing these instances of indexed copy counters. So I'm actually comparing the copy statistics. Let me also get a normal value, just to make sure that also works. And it does. Great. Now let's get back to TupleCat, which is where this whole testing detour started. We again create a tester with builder and 2 copy counters. I'll call it tuple with 2 args, as we only test the 2-argument version of TupleCat. I'll build 2 bits of Q tuples and 2 std tuples. Let me make this all nice and symmetric. That looks much better. Now we do a TupleCat, forwarding our 2 input tuples, and we do the same thing for our std variant. Something like that. And now, lastly, we want to compare these. Assert get0 of the bits of Q t12 should be equal to get0 of the std t12. And now I get some compilation errors. I forgot to invoke tester with builder with 2 as the template argument. So I tried to pass as builders for 1 argument. And even worse, I typed tuple instead of TupleCat. That's the risk of recording a live coding session. There we go, TupleCat with 2 arguments passes. Now we can get rid of these asserts down here. Okay, before we continue to create a generic TupleCat, I want to quickly show you what would happen if I would have made a mistake in implementing the 2-argument version of TupleCat. For example, if I would have forgotten to use std forward here, I will get a bunch of errors when running the test. The framework shows us where the assertions are failing. In this case, it is the comparison of the gets of the elements with index 1, the copy counters. And it also shows us the configuration of the builder when the test failed. Here we see the first failure happened when the builder was invoked with an rvalue reference and an lvalue reference. If you look through this list of output, you immediately spot the pattern. Every time an rvalue is involved, the test fails. Sounds like rvalues are being copied instead of moved. I probably forgot a forward somewhere. For the last bit of polish, it might be nice to actually check if all elements of the bits of Q and standard tuple are the same, instead of just checking index 0 and 1. If get would have accepted a runtime index, we would be able to write a small for loop like this. This of course doesn't compile. To make this work, we need a compile time for loop. I already implemented this and added it to our metaprogramming library, as it was needed for the test framework. Let me show you how to use it, and then we'll see how it was implemented. Just like with a normal for, we pass the start and end index, but now these are template parameters. I've currently hard-coded an increment by 1 for every iteration of the loop, so you don't need to specify that part. Then, to specify what happens in the body of the loop, we pass a lambda that takes the index as an input. Here we are using that lambdas are automatically const expr whenever possible, allowing them to be executed at compile time. The index that gets passed to the lambda is actually an std integral constant. So to retrieve a compile time integer from it, we should access its value member. And that's all you need for a compile time for loop. So let's see how this static for is implemented. It is a simple const expr function that uses recursion to do the looping. It checks if first is smaller than last, and only if this is the case will it call the function with the integral constant value of first, after which it recurses with an incremented first. Simple but effective. Okay, now let's go back to our TupleCat and look at implementing a multi-argument tuple. We'll create another test with builder, this time passing 3 as the template argument, to indicate that we'll be using 3 arguments for the function that we are testing. This will of course mean that this test is going to be executed with builders for 4 to the power of 3 equals 64 combinations of arguments. This is quite a lot of executions already, so I would recommend not going beyond 3. If you do need more inputs, it's better to think a bit about what the specific corner cases are that you want to test your algorithms for, and just test those instead of every possible combination of inputs. So let's update the build calls to take a 3rd argument, and then the TupleCat function calls with the 3rd argument. Of course, again forwarding it so we can preserve the value category. This is of course going to fail when we try to compile, because our current version of TupleCat only supports 2 arguments. Indeed, if I scroll up, no matching function for call to f in our tuple get impulse struct. So let's go there and fix this. Now we can of course add an overload that takes 3 arguments to our tuple get, but that doesn't really scale. We'd have to add another one for 4 arguments, one for 5, etc. In these cases, your first thought will probably be to use a variable template, which makes sense. But then passing this to cut from indices would become problematic, as you'd end up with a variable number of index sequences, which each have a variable number of indices in them, a sort of parameter pack of parameter packs, which is something C++ doesn't support. So we need to change our approach a bit. Just like we did back in episode 5 when writing our popback function, we will use recursion and gradually build up our output tuple as we recurse. We update our template to include a red tuple, the tuple that we'll be returning in the end. The first tuple which we want to add to our red tuple we'll just call tuple, and we'll use a parameter pack to represent any remaining tuples after that. We can still use our get from indices to add our tuple t to our output tuple red. But now we also need to recurse once we've done that, to finish putting the remaining tuples in our red tuple. So we put the output of our get from indices back in f and forward the remaining tuples. If we now compile, we should see an error that there's no matching function called to f. This is because once we've recursed enough times, we'll only have the return tuple remaining, and there is indeed currently no overload for f defined that takes only a single tuple. So let's add this base case. If f is called with only the return tuple, we should just return it. And now this should all compile. And indeed it does. However, when executing the test, we see that our assert statements are failing. As a matter of fact, even our 2-argument tuple get test is now failing. So we completely broke our tuple get with this change. Let's see what's going on here. I'll temporarily disable the 3-argument tuple get test just to reduce the amount of spam, and now I'll output the stats of our copy counters. This should show what's going on, because, as you might have already realized, these asserts are failing because too many moves are made, not because the output tuples contain incorrect data. Indeed, if we look at our output, we see that, with 2 arguments, our tuple get makes exactly 2 moves too many. This is clearly a pattern among the different invocations. So, what is causing these moves? Well, we are passing this red tuple around. And since it is the output of get from indices, it is an rvalue, leading to the forward statements acting as moves. Usually moves are quite cheap, but no moves are always better than some. So let's see how we can update our implementation to avoid unnecessary moves. Instead of building up our return tuple directly, we are going to use an intermediate representation while we recurse. We'll build up a forwarding tuple that is going to store lvalue and rvalue references to the elements of our input tuple. Only once we are completely done recursing and we have created a forwarding tuple with references to all the input elements, will we convert this forwarding tuple to our final output tuple. I'll start by just renaming some things. The red tuple will become a forwarding tuple, fwd for short. We'll still pass the forwarding tuple and a first tuple to a function that is going to add one to the other, but instead of using get from indices, we'll create a new function, concat with forward tuple. In contrast to the get from indices function, concat with forwarding tuple is going to take the index sequence as template arguments instead. The idea is still the same. We pass our forwarding tuple and the tuple we want to add to this concat function. And then we recurse. So this will recurse on and on until everything is in the forwarding tuple, at which point we get to the overload below. And here we will need to translate our forwarding tuple into the real output tuple before returning. So we'll add a make tuple from forwarding tuple call here, which also takes an index sequence of the size of our forwarding tuple. Now let's fill in the implementation of the missing functions. First, concat with forwarding tuple. As template parameters, we will have an index sequence for the forwarding tuple and one for the tuple we want to add. And now we create a partial specialization to give us access to the indices in these sequences. And again, we create a member function template f, taking the 2 tuples as arguments. The implementation of this f is quite simple, as we can make use of the forward as tuple function. This is a function which exists in the standard library, but we have not yet added it for our own tuple, so we'll do that in a bit. With such a function available, however, we can just do a get for all the elements in both tuples to create a forwarding tuple. we'll define forward as tuple outside of the detail namespace, as we might want to use this in other places as well. Forward as tuple takes the elements to forward as forwarding references and constructs a tuple from them. But the trick here is that we explicitly specify the element types of our tuple. Remember how forwarding references deduce to either an rvalue or an lvalue reference type, depending on the value category of the input? So by adding the two ampersands to the t's, we are creating a tuple whose elements are also going to be either lvalue or rvalue references, depending on whether our inputs were lvalues or rvalues. This is important, as we need to know whether we should move or copy when turning the forwarding tuple into the actual output tuple once we are done building it up. Now, I see my linter is showing me that I made some small mistakes. I forgot to expand the parameter pack when passing the elements of our tuple. Let me fix that. Okay, so now we are building up this forwarding tuple using the elements from our input tuple. And then at the end we need to convert it to a normal tuple. So let's write this create tuple from forwarding tuple function. Again, we are using a struct template with a partial specialization. And since our forwarding tuple contains lvalue and rvalue references, we can just get those elements and pass them into the constructor of tuple. This will lead to copies and moves being executed as needed. If I now build, I notice I made another small mistake. I forgot to actually call the fMember function in the concat with forwarding tuple call. And now it all builds. And from the debug output, which we still had lying around, we see a confirmation that indeed we have the correct number of copies and moves. Now let's also enable the tuple-cat test with 3 arguments. This is the moment of truth. Is our new implementation also optimal for more than 2 arguments? And indeed it is. All tests pass. So we've now successfully created a generic tuple-cat function that operates on our own tuple type. We have also extensively tested this tuple-cat using the new testing framework, which means that we are now ready to explore some more advanced tuple manipulation algorithms, which are not in the standard library. But this is something for a future video. You might have also noticed that our compilation times have skyrocketed in this episode. This is mainly caused by all the different builder types that are instantiated by our test framework, and is a common problem when using a lot of metaprogramming. In the last part of this series, we will be looking into the different operations a compiler does when processing metaprogramming code and which ones are the most expensive. We will then use this knowledge to develop some high-performance metaprogramming techniques. So make sure you subscribe, as the coolest part of the series is yet to come. See you next time.